Okay, today's video is International A-level paper, Physics Unit 2 on waves and electricity. Okay, so I'm doing this for two of my students who are taking actually the linear exam. I've used these questions to help them prepare for their exam on Wednesday, which is the same time as the Unit 2 International A-level is on. So they're doing core Physics 1, which is electricity with mechanics. So I'm only going to go through the multiple choice and the electricity questions. So Sophie and Devon, if you're watching, don't watch until you've done the practice paper I made for you. And then you can use this to do your corrections over the weekend. Okay, so let's have a look. So those of you who are doing Unit 2 IAL on Wednesday, same day as the electricity and mechanics for the Edexcel linear, you did your Unit 1 today. I'm sorry I couldn't get you the January 25 paper in time. Yeah, just because I'm currently focusing mainly on the linear exam. So I just can't keep up with the demand for videos. Okay, so in advance, if you're watching, don't forget to like it, share it, and make sure you're subscribed because more videos are coming. And by the way, if you're doing linear, you should use the International A-level papers because there aren't as many linear papers because it's once a year. Okay, so here's the multiple choice questions, and question 1 is gives you the formula for current, yeah, in a conductor as I equals NQVA. So this is a knowledge question, and they want you to know the meaning of N in the equation. Well, this is, because it's a knowledge question, you just got to know it. There's only one right answer. It's the number of conduction electrons per meter cubed. Yeah? So the answer is B, and you can look through the others, and if you don't know this, it's just helpful when you're revising to go through as many multiple choice questions as you can. Question 2, they want you to know about current again, so current in a wire. They're telling you the charge of, they're going to ask you about the charge of an electron, and basically they want you to say how many electrons will pass a point in a wire or on the wire in a set amount of time, t. Okay, so basically the equation you need to focus on is I equals Q over T, and you know that Q is basically the number of electrons. So you multiply N by E and you'll get the total charge in coulombs. If you then replace Q into this equation with NE, you can make this equation up. So current will be N times E over T, and they want you to know how much is N, the number of electrons, so that's N, yeah, in this equation. So make N the subject of the equation. N will be IT over E if you can do the algebra, which gives you the answer D. Okay. Number 3, it's a car has a distance sensor that uses a pulse echo technique. That means it sends out a pulse to determine the distance to a nearby object. So the car has this method of doing it. The sensor in the car sends a pulse out, emits a pulse of sound, and then detects the echo, yeah, after a time t. So obviously the distance traveled in is 2s because it has to travel there and back because it's the time for it to be emitted and detected. So it's going there and back again, there and back. Okay, so the distance it travels is 2s. So they want you to work out which expression gives the distance between the car and the object. Okay, so obviously distance is speed times time, or velocity times v. The speed is given as v. Okay, So you multiply that by time, but obviously it's got to go there and back, so you then have to divide it by 2 to get the right answer. So it's S equals Vt over 2, which is 0.5 Vt. Okay, so the answer is C. Question 4 is on waves. So 2 waves on a string move towards each other. Yeah, so they're moving towards each other at the same speeds. So I've put the 2 arrows to represent these 2 peaks moving together. Yeah, or the 2 troughs moving towards each other. Okay, so they have the same wavelength, and they've shown you how much half a wavelength is. Yes, and it shows the waves on the string when they're half a wavelength apart. Which of the following shows the string when both waves have moved a distance of half a wavelength? Okay, so if they both moved a distance of half a wavelength, yeah, you can see how much the trough will move towards the middle, and it has to be the same distance as this. So once you see that, you can see the 2 troughs will meet when they move half a wavelength towards each other. Okay, so 2 troughs meet. So you're looking for the superposition, yeah, of 2 troughs. They superpose. That means they add up, or in this case, they create a bigger trough. So if they both are going, the troughs meet at that time in the middle, yes, you're going to get a deeper trough. So the answer is B. Question 5 shows a circuit including a thermistor. Yeah, so the symbol for a thermistor is that. Looks like a spatula going through the resistor, and they want you to explain the changes in the ammeter as the temperature decreases. So as the temperature decreases, we know that the thermistor resistance will decrease. If the resistance will decrease, the current will decrease. So the change in the ammeter is due to the temperature changing the resistance, increasing the resistance, and we're looking to see which one's correct. So the number of conductional electrons decreases, yeah, because it's a negative temperature coefficient thermistor, and the ammeter reading decreases. Yeah, so the answer is A. If you want to read through the other ones, you can see where I've put an X, why it's wrong. We know the ammeter isn't going to increase, so that's wrong. We know the electrons aren't going to increase, the conduction electrons will decrease. So you're looking for conduction electrons decreasing. Again, here they got conduction electrons increasing. Okay, so the only one with the 2 ticks is A. Then the next question is 3 identical resistors, yeah, in the circuit as shown. 2 of them are in parallel. If they're identical, 2 resistors, identical resistors in parallel, will actually create 2 paths where the resistance actually halves, because the current will be going in each path. So we know that the resistors in parallel will be halved, and then you add it to the resistance next to it in series, and they've told us that the cell has an EMF of E epsilon and negligible internal resistance. So there's no, we can ignore the resistance of the cell, which is the following is equal to the reading on the voltmeter. So the voltmeter reading, how much will the share of the single resistor be? So they want you to work out how much is the share of the single reading. Well, the voltage reading will be the resistance R divided by the total resistance of the circuit, which is, I'm going to put it in green, there's the total resistance of the circuit, yeah, in a diagram, and the total resistance is R plus half R, yeah, because this is half R, add it to R, and you get 1.5 R. So we know what the total resistance is, and we know the ratio of the resistances, so the answer will be R divided by 1.5 R. Yeah, the R's cancel out, and you multiply it by the voltage of the supply, which is the EMF, so it will be equal to 2/3. 1 over 1.5 is the same as 2/3 of epsilon, which is the EMF, so the answer is C. Question 6 done. Here's what they give you in terms of the mark scheme. I'll let you have a quick look at it while I have a sip of my tea. Okay. And then question 7. Question 7 again has got a wave of amplitude A on a string. Yeah. P and Q are 2 points they want you to consider. And it's a stationary wave. So which row of the table is correct? The phase difference between P and Q is 0 because they're going up, and therefore they'll also go down together. So they're in phase. So in a standing wave, this bit goes up together and down together. Okay? And the second one is the amplitude of P and Q will not be equal to A because they're not in the center of the antinode. They're to the side of the antinode. They will be less than A. So the answer must be B because it's the only one with 2 ticks. Question 8. It's got 2 lengths, D and L. Yeah. And they've attached an ohm meter. And they want to investigate the resistance of a piece of copper wire, yeah, of length L. So obviously the resistance is proportional to the length, okay, and they want you to work out which gives the total resistance of the length L. So they want you to work out R total, whereas right now it's a fraction of the total. The ratio of the total to the resistance when the ohm meter is across D, the length D, which is not the total, will be, as it's proportional, the ratio of the resistances will be equal to the ratio of the lengths. So the total resistance corresponds to L and R corresponds to D in the same fractions. So you just change the subject to put R total on its own, and you get L over D times R, which gives you the answer D. Question 9 is energy levels in an atom. So the diagram shows the energy needed for an electron in the ground state of a mercury atom to move to different energy levels in the atom. So the ground state is the bottom state. The photons have this much energy in joules. So you got to convert this photon energy, HF, into electron volts. The way you do that is you divide the joules by the charge of an electron, which is given to you in your data sheet, and you'll get the equivalent amount in electron volts. And you'll notice that this causes excitation from the ground state up to the energy levels, which corresponds with the photons which are absorbed. So basically those photons will be absorbed by mercury. So what's the question? The question says, which of the following gives the number of different frequencies of light that could be emitted? Okay, so it's absorbed the photon, but what goes up must come down, and what comes down, it can go from the 5.46 state down 1 level, down 2 levels, and after it goes down 1 level, it can go down another level. So there's 3 possible emissions that can be created. So the answer is B. Okay? That's question 9. So in the IAL, there are 10 multiple choice questions, and in the linear, there are 8 multiple choice questions. So it's slightly different, but I think they actually use more or less the same bank of questions, and they kind of borrow from each other every now and then, I've noticed, or very similar questions. Okay, they obviously must have a different lead examiner setting the papers. They are slightly different. The style is slightly different. But the IAL have 3 exams a year, so it's worth Edexcel International linear students using them to practice. A student connected the circuit shown, so you've got 9-volt battery with an internal resistance drawn here. Okay, so the reading on the voltmeter is 6 volts. That means we know the current automatically is 0.6, but then I notice when you put 0.6, they want it as a fraction, 6/10, yeah. So if it's 6 volts and 10 ohms, the current will be 6 divided by 10. So they don't want decimal because you can see the answers all as fractions. So when I did it, I then had to swap it back. So sorry about the confusion. Which of the following expressions gives the internal resistance of the battery? So we know that the EMF must be the current outside, the current times the resistance outside plus the current times the resistance inside. In other words, the current times the total resistance of the circuit, external resistance and internal resistance. So when you do that, EMF was 9 volts. If you look at the diagram, EMF is 9 volts. The volts meter is reading 6, so that's equal to IR, and therefore the current we know is 0.6, and this I should change to 6/10 to make it into the form that the answers are given. So when you do that, you'll see that I put internal resistance as the subject, yeah, divided by 0.6, so I'm actually dividing by V over R, which is current, yeah, so I'm dividing by 0.6, which was the current, when the current, as I said, is 6/10, okay, so I've changed it back at the bottom to 6/10, so it's 9 minus 6, the difference in the voltage, yeah, between the EMF and the terminal potential difference, so the voltmeter reading, divided by 6/10, so if you divide by 6/10 as a fraction, yeah, divided by, the 10 goes to the top, 6 stays at the bottom, that's just algebra, so you get 10 times 9 minus 6 in brackets, divided by 6, and the only answer that looks like that is A. Okay? So that's the multiple choice questions done. I hope you found that useful. Don't forget to like, share, and subscribe. We're now over 1,200 subscribers. So I know often you ask questions. I try to get back to everyone. There is now a membership system available. And if you are a member, you get responded to quicker. So that's an advantage. I think it costs a little bit, like 15 dirhams, which is the UAE amount that YouTube charge for becoming a member. That's another way to show your appreciation. I mean, I'm not doing this primarily for money, but obviously they take a lot of time to make these videos. So if you do want to become a member, feel free. Otherwise, I still answer questions. So if you're a subscriber and you've asked a question, eventually I do get to answer it. Okay, but make sure if you're asking a question that you say what minute of the video and which question number you're referring to. Some of you are asking the question while it comes to you, but you haven't told me which question you're referring to. I can't look through the whole paper again. Okay, so the next question. So I'm only doing today the electricity questions. So this one is on the de Broglie wavelength, yeah? So I'll come back and do those in a follow-up video, okay? So there's the question 11. If you want to just have a look at the mark scheme, you can. Question 12 is also about light intensity, yeah, incident on a solar cell. So it kind of is electricity, but I haven't covered this in this run through. Yeah, there's the answer to that question. If you want to go through it on your own, you can. Stop the video where necessary. Here is one of the questions I've put in for the practice exam at the request of my students. So question 13 is an electrical cutting tool which uses heated metal to cut through polystyrene. Now, I remember having one of these years ago, I mean, way before you lot were even born, and it was quite fun cutting polystyrene with this hot wire. You basically had a battery which would heat up the thin bit of wire, copper wire, and you could just make shapes out of the polystyrene. Okay. The temperature of the wire increases when the current cutting tool is switched on, just like I just explained. Explain how the resistance of the wire changes as the temperature of the wire increases. Okay, so a wire normally would have a constant resistance if the temperature doesn't increase. So when you're doing the component of a wire or a fixed resistance, normally we say it's ohmic. But if you let it get too hot, it will become non-ohmic, and it has a temperature coefficient, just like a thermistor does, except the resistance increases with temperature. Why? Because if you increase the temperature, the lattice vibrations will start to increase. Basically, the energy that goes into the material causes heat. The heat is thermal store of energy, which is vibrational energy. So the lattice structure vibrates. So the collision rate between the conduction electrons and the ions increase. Yeah. So because of that, the resistance increases. Yeah. So it says explain how the resistance changes. So changes to a scientific explanation of increases. So the key word is increases. And why does that happen? Because the lattice vibrations impede the electron drift velocity. They impede the electrons, so the drift velocity goes down, so current goes down, so we say resistance has gone up. Okay, hope that makes sense. So remember, when you're writing these answers out, you need to make sure you have all the key terminology. Don't use it, don't use they in your answers. I've just put the bullet points down. When you look at the mark scheme, you'll see I will have got the 3 marks for those 3 bullet points. Part B then goes on to look at the resistivity equation when the wire is at the correct temperature for cutting. So in other words, it's hot. The resistance of the wire is this many ohms. Yeah, the wire has a circular cross section. Yeah, they're giving you the diameter of the wire, so these are length. They're giving it into millimeters. You've got to change it into meters, and you've got to work out the cross-sectional area. Yeah, using pi d squared over 4, which is the same as pi r squared. But the main part of the question then, after you've worked out the area, is to calculate the resistivity. Yeah, at that temperature, which they've then given you the length of the wire as well. Yes. Now you know that resistance is rho L over A. You want to find rho, so change the subject of the equation again. Yeah. We know the resistance, so the resistance is given to us, 0.67. We worked out the area by doing pi d squared over 4, so you'll get a mark for doing that. Yeah. There's 1 mark. Put the number in, divide it by the length. Yeah. And you get 9.76 times 10 to the minus 7 to 3 significant figures, and you can probably round it up to 9.8 times 10 to the minus 7 ohm meters. Don't forget the units, okay? It's just good practice to always remember the units, okay? So I think probably 2 significant figures is appropriate because the data is all given to 2 significant figures. So that's another question done. There's the mark scheme if you want to have a look at it while I take another sip of tea. Yes, it's green tea. Okay, question 14 is another question on waves, diffraction grating, because my students aren't doing the Unit 2 exam, they're doing the linear exam, which is, in the linear exam, paper 1 is mechanics and electricity. So I've just focused on the questions that they need for their exam next Wednesday. Okay, and in the linear, they don't take a January exam, they then do waves and materials in paper 2. Okay, so this would be in their paper 2, but it's in the international unit 1. So international A-level is in units, and the Edexcel is in paper 1 and paper 2. AS Core 1 is called, and AS Core 2 almost identical content. There's just one difference, and I will tell you in a future video. Okay? So this is the answer to the waves equation. Yeah, so if you want to have a look at it in this run through, you can without my model answers, although I will add them in before the Unit 2 exam next week. So this is a January 2025 paper. It's the most recent exam taken by students in January. A student connected the circuit shown. So in a circuit, you got a battery, you got a lamp in parallel with a resistor, and you're measuring the current through the lamp, and you got the voltmeter across the lamp, yeah, and the ammeter. But remember, ammeter uses almost no current, so therefore the voltage reading is basically the voltmeter, the voltage across the lamp and the 15 ohm resistor, which is in parallel to it. And here you've got a variable resistor, which allows you to alter the amount of voltage that the lamp gets, so you can make it dimmer. So it's like a dimmer switch. The student adjusted the variable resistor, as I just explained, and recorded the corresponding values of current in the ammeter and potential difference for the lamp. The graph is shown below, so you can see it's a curved shape. It's not ohmic, okay? So what are they asking for? The student adjusted the variable resistor so that the voltmeter reading was 3.6 volts, okay? So show that question means you've got to prove it mathematically, yeah? So whenever it's show that, I put this bubble around it. Show that the combined resistance, yeah? Combined resistance of the filament lamp and the resistor in the circuit, the ones in parallel, in other words, are resistors in parallel, the resistances in parallel is about 5 ohms to the nearest significant figure. So what you've got to do, first of all, is use the graph to find the current, yeah, that corresponds to 3.6 volts. So you can see I've drawn it from 3.6 volts. I've drawn a line up with a ruler and then a line across and read it off as halfway between two squares, which means it's 0.47 amps. Okay, once you know that, you know the resistance of the lamp must be equal to the ratio of the voltage to the current, and therefore we know the resistance of the lamp. We already knew the resistance in parallel with it was 15 ohms, so you got 15 ohms with about 7 point something ohms. So remember, resistors in parallel reduce the total resistance. You then use the resistors in parallel equation, yeah, and if you use it properly with the correct numbers in, you will be able to show that you get the two fractions, and it comes out to 0.197, but you need to inverse that, and when you do that to 3 significant figures, it's just over 5 ohms. Therefore, to 1 significant figures, you have shown that, yes, it is what they asked in the question, which was show that it is 5 ohms. Okay? Hope that makes sense. The next part of the question is the EMF of the battery was 4.5 volts. That means if we know the EMF was 4.5 volts and the lamp, the parallel section, had 3.6 volts, then we know if this was 3.6 volts, the rest of the EMF must be across the rest of the resistances. So this would be 4.5 minus 3.6 volts, just for reference, okay? If there's no internal resistance, yeah? Have they actually mentioned internal resistance? Yeah, negligible. So you can ignore the internal resistance. So you know that the voltmeter reading was 3.6 volts. They want you to determine the power dissipated in the whole circuit. So we've got to use the 4.5 volt part, and we need to know the total current. Well, the total current is the current that goes through the variable resistor, because what happens is the total current will be equal to the voltage across the parallel section divided by the resistance of the parallel section, which we worked out was 5.08. So you put that in there with the voltage that we know. So the ratio it tells us the current coming out of the parallel section must be 0.709 to 3 significant figures. So that's a total current in a circuit. Let's have a look why it's a total current in a circuit. So if the resistances of the parallel, we knew some of it's coming through here, and the parallel sections, so some current is going through the resistor, and some of it's going through the lamp, and they join up here. So whatever is the total current for this section, the total current is the sum of the currents through the two resistors. So if we know the total resistance, which we now do, and you know the total resistance, then the total current coming out of there will be equal to 3.6 volts divided by the approximately 5 ohms, 5.0, whatever it was, 8 was it, ohms, and that will give you the total current that's coming out of the parallel section. Therefore, it's a total current going through the resistor, yes, as well. So it's the current of the whole circuit, okay? Once you know the current of the whole circuit and you know the voltage of the whole circuit, yeah, you know the power dissipated is going to be voltage times current. The total voltage divided by total current. Total voltage is the EMF. Total current we just worked out. Multiply them together to 3 significant figures. That's what you get. You can round it up to 3.2 watts. Okay? So that's another 7 marks done. There's the mark scheme. If you want to pause the video, have a look. They've done alternative methods. Okay? But I think the way I've done it is probably the easiest. Okay. The next question is also electricity. So this is what my students are preparing for. This is an LDR connected in series with a cell. Okay. Looks like this time they are including the internal resistance. So first of all, they love asking this question: what is meant by the EMF of a cell? Well, the EMF cell is the energy supplied by the cell per unit of charge, because 1 volt equals 1 joule per coulomb. Yes? Okay. And then the second part of the question has an asterisk. What does that mean? It's a qualitative 6 marker. Yes? So don't be scared by these. You just got to read the question really carefully. The voltmeter measures the terminal potential difference across the cell, which is the voltage available to the external part of the circuit, which is the LDR. And it says, explain how increasing the intensity of light, yeah, obviously incident on the LDR, affects the reading of the voltmeter, or on the voltmeter they've put, okay? So how does it do that? Well, the intensity of the light increases the number of photons per second, yes, incident on the LDR. So more photons landing on the LDR, and remember, each photon has energy, and each photon can give its energy to electrons. So this causes an increase in the number of energized conduction electrons, because conduction electrons have enough energy to escape their atom and to help in the flow of electricity or flow of current. So N increases in the I equals NA V E, where E is the charge of an electron. So the bigger the N is, the more current you'll have, okay? So this decreases the resistance of the circuit, yeah, externally. So the LDR resistance decreases. If the LDR resistance decreases, the current in the circuit must increase, yeah? And if your current increases, so this is why sometimes students get confused, if the current through the cell also increases, yeah, it leads to an increase of lost voltage inside the cell, because remember, a cell has internal resistance. So if the current is the same everywhere in a series circuit, you're going to get some voltage, PD, across the internal resistance of the cell itself. And this is what's known as lost voltage. Yeah, that means before it can be used, you already have, whenever current is drawn, you will lose some of your voltage. And this is a core practical, which my students have done. And the difficulty is explaining it in all these bullet points. So you can see I've got 1, 2, 3, 4, 5, 6 arrows corresponding to what I think are worth the 6 marks. Therefore, the terminal potential difference decreases because we've lost voltage inside, so the EMF is reduced by the amount of lost volts. The lost volts is IR. So the IR is how much the EMF reduces by, so the voltmeter reading will decrease. Okay? Now, that will definitely get you all the 6 marks the way I've explained it to you. Now, you need to practice explaining these things, and the more questions you practice, even if you've repeated doing the same questions, just make a set of notes on questions like this, because they do have a commonality between different papers, that they ask similar questions, and you've got to basically be able to explain your reasoning logically. Okay, so there's the mark scheme. Here's the 6 marker. They explain to you how they mark it. They're looking 4 marks for the content that I've given and 2 marks for your reasoning. So if your answer shows a logical and coherent structure with clear linkages, fully sustained without any confusion, you will get the 2 marks from your way you're answering it. And if there's a little bit of confusion, you could just get 1 mark. Yeah, and you can see this is the content they're looking for, which will be very similar to what I've explained. And I'll let you stop the video and have a look to see if what you've written merits a mark or not, and you have to judge that for yourselves. Okay, so here's another question on standing waves. Yes, on a vibrating string, which is another core practical, but my students don't need it for next Wednesday's exams. They'll need it for the following Wednesday's exams. But for those of you doing IAL, I will plan to do these in a separate video. Okay? So you can have a look at it later. So it's a long question, 10 marks. There's the mark scheme. I'll let you pause it if you want to just look at it before I do the second run through. Okay, question 18 is also about waves, fiber optics, refractive indices, and something between air and glass, not drawn to scale. Yeah, so I will go through this in the next run through. I'm just having a look at it while I'm flicking through it with you. Yeah, so it's a part C as well. There you got fiber optics. And then you got some cladding around the fiber. It's 13 marker, so I didn't do that in this paper. And there's the mark scheme. I haven't read the full question because it's quite a long question, this one. So it will require a separate run through. Question 19 also, you've got a photocell, so it's not needed for my students in Wednesday's exams, but it is for international A-level students. I plan to do that before Wednesday, I hope. Okay? So you can have a look at the question. You might have done this paper already. I'll show you the mark scheme. 5 marker here. Another explain what the observations are. Yeah, the nature of light. Okay? And there's the answers. 8 marks, and then there's a part C. Stopping potential, I think, and that's the end of this run through. So I hope you found that useful. If you did, give me a thumbs up, share it with anyone in your school who you think will benefit, and make sure you're a subscriber. Okay? Thanks for watching. Catch you next video. Bye for now.